Welcome everybody. Welcome to this analog design lab. Today we are going to discuss about design to a series regulated DC power supply which are widely used in different applications. Let us try to check what is the general problem. The general problem is like this: design and construct a series regulated DC power supply with specified output voltage and load current. So before we start our design, we need to know the meaning of a regulated power supply. A regulated power supply gives a DC output voltage which is fairly constant irrespective of changes in the AC supply voltage or DC load current. If you are talking about a power supply, battery comes into our mind, which can gives you a constant voltage level, but that cannot also provides a constant supply when we are going to vary the load resistance RL. Let us check this circuit where Ri is the internal resistance and RL is the load resistance. The output voltage can be write like this: the output voltage, which is fairly uniform whatever be the load current, but this is ideal. This equation shows with increase in load current your output voltage will gradually decrease like this. So that means output voltage is not maintained on the operating load current. This will happen for a battery also. The internal resistance is mainly responsible for that. Also, if you are going to use battery for different applications, their power is limited. So what you can do, we can use a source where a power supply that can be designed from an AC source to provide some DC output. This type of DC generation we have already started in our design 1 using rectifier. 220 volt 50 hertz AC source is connected at the input of the power supply, and we can design to get some specified DC voltage. Ideally, we may expect a constant output voltage irrespective of time, but practically there will be some fluctuations which we have studied in our design 1 and we call it ripple. Like battery, with increase in load current, the output voltage will decrease gradually following this relation. And in certain applications, you cannot go beyond some load current. We have to restrict within IL max. Now, for a practical power supply, someone can calculate the load regulation, and that can be defined as VLN minus VFL by VFL into 100. So where VNL is the no load output voltage and VFL is the full load output voltage. So that is the measurement how your power supply free from load variation. Okay. So ideally load regulation should be 0. Now let us try to check what will happen if you vary the input AC source. Practically you can expect some variation in the AC source end also. Ideally you want a constant output voltage irrespective of the source voltage Vs, but practically what you will get a variation over the Vs. So corresponding line regulation someone can calculate using this formula. We call it line regulation or percentage of line regulation. So that can be defined as delta V output by delta V in into 100. Line regulation can be defined in terms of percentage per voltage.
Let us explain the block diagram of a regulated power supply.
The function of rectifier is to convert 220 volt AC to a DC. This part already we have discussed previously in our design 1, where the transformer can gives you some full sinusoidal voltage and the rectifier gives you either full wave or half wave rectified output. The function of the filter is to develop some pulsating DC containing some ripple. Depending on the filter characteristics, the ripple characteristics will improve. So you may get a constant DC at the output of the filter. These 3 blocks already we have discussed. What are the different types of voltage regulators? There are 2 categories: linear regulators, switching regulators. Linear regulators are 2 types again: series regulator and shunt regulator. Why it is called series? Because the regulator is in series with the load, and in shunt regulator the main controlling unit is in parallel with the load. Now what about the switching regulators? The transistors are not in active region. Their basic principle depends on switch on and off conditions. That's why they are most efficient regulators. If you consider the series regulator, it consists of several building blocks. So main control unit is here, which is controlling the output voltage. You should have some sampling circuit, some error detecting circuits, which will basically produce some error depending on the sampled output voltage and some reference voltage. The difference will produce some error. This error signal will control the control unit. The negative feedback mechanism to stabilize the output voltage. This is the basic working principle for this type of series regulators. Here is some design of some series regulator using op-amp. Op-amp actually functions as an error detector. Q1 transistor acts as a control unit. So for sampling, we have used some voltage divider network here. For this reference voltage, someone can use a Zener diode in reverse breakdown that will provide some constant voltage across this Zener in reverse bias. Some other versions are of transistor series regulators. This is the building block for the shunt regulator. Basically, the load current controlled by this ISH, which is the current to the control element. If you drain more ISH, IL current will be regulated. In shunt regulator, the regulator is actually connected parallel to this load, and the load current IL actually controls by this shunt current I. This shunt current again controlled by this controlling element. Actually, the sampling circuit samples the output voltage and compares it with the reference voltage to produce some error signal. Finally, the control element actually controls this output voltage or the load current. Here, a op-amp based shunt regulator has been shown. Op-amp functions as the comparator circuit, and the control element is Q1 here, which is parallel to this load. R1, R2 is a voltage divider network, acts as a sampling circuit. The Zener diode has been used to produce some reference voltage. Here is some transistor based shunt regulator. Now let us discuss about our assigned problem, where you asked to design a series regulated DC power supply with some rated load current. The specific problem is like this. You have to design one 15 volt DC regulated power supply for maximum load current 250 milliampere. The design is like this. This first part already we have designed in our design 1, where we have designed one rectifier circuit. The series is our new job. This circuit consists of transformer, rectifier and filter, which has been covered in design 1. The next part is the regulator. If you compare with op-amp based regulator circuit, the transistor Q2 functions as the element. We call it pass transistor. Most of the current will be passing through this, so wattage rating of this transistor should be very high. The transistor Q1 actually functions as an error detector. The rest of the circuit is very similar to the op-amp based series regulator circuit. This is the complete circuit diagram. Our job is to calculate each and every parameter required for this circuit based on the specifications given. So V0 is the required output voltage. Assuming the unregulated voltage is 20 volt. So from 20 volt we have to design a regulated voltage which is 15 volt, and maximum rated load current is equal to 250 milliampere. Because of some laboratory limit, we have to use some Zener diode and transistors. Let us use a 5.6 volt Zener diode, and we are going to use CL100 as the pass transistor, and for the error amplifier purpose we are going to use SL100. HFE or beta values are respectively 50 and 125. This is the detailed calculation for different circuit components. Let us try to calculate the value of R2. So that can be done by applying KVL at the Zener circuit. Zener diode is 5.6 volt, 1 watt. That means maximum Zener current allowed can be calculated using this formula. It comes out to be 166 milliampere. Let us take approximately IZ equal to 10 milliampere, which is required for the Zener breakdown, and IZ should be less than IZ max, which is 166 milliampere. Let us take the collector current flowing through this Q1 transistor is equal to 5 milliampere, and I double prime is equal to 5 milliampere. So the value of R2 will be V unregulated minus Vz by I double prime, comes out to be 2.88 kilo ohm. Similarly, we can calculate R3 and R4 value. The feedback factor beta is equal to Vf by V naught, and it can be write like this, and it 4.2 volt. So beta equal to 4.2, which is again can be expressed in terms of resistors R3 and R4. After simplification, R3 will be 1.38 R4, and assuming ID equal to 5 milliampere, IV1 can be negligible, therefore R3 plus R4 equal to 3 kilo ohm, and you can calculate R3 equal to 1.74 kilo ohm and R4 equal to 1.26 kilo ohm. You can also able to calculate the R1 value. You can write IB2 is equal to IE2 by beta 2. Here IE2 can be written as ID plus I0, and after calculation it is 5.1 milliampere. Here ID equal to 5 milliampere, I0 equal to 250 milliampere, and beta 2 equal to 50 as provided. Let us consider IC1 is equal to 5 milliampere required for the active region of the transistor Q1. Therefore, I prime is equal to IB2 plus IC1 is equal to 10.1 milliampere. Applying KVL, you can able to calculate I prime R1 is equal to 4.3 just by simplifying this equation, and R1 is equal to 425 ohm. It is necessary to estimate the wattage rating of all components used for this design. Let us start with Zener diode. Since we have assumed that IE1 approximately equal to IC1, so the maximum current through the Zener diode will be 10 milliampere. So the maximum power dissipation can be calculated in this fashion: maximum current multiplied by Zener voltage. This comes up to be 56 milliwatt. Similarly, for the transistors, for the Q1 transistor, the power dissipation will be 50.5 milliwatt. For the pass transistor Q2, the wattage rating will be 1.275 watt. Same thing we can do for the resistors also. The wattage rating for the resistors can be obtained using I square R formula. For R1, the wattage rating is 43.3 milliwatt. For R2, it is 72 milliwatt, R 43.5 milliwatt, and for R 31.5 milliwatt. At the same time, we need to calculate the wattage rating requirement for the load resistance. The maximum wattage rating for the load resistance can be obtained using this formula: V0 into I0 max, that is 3.75 watt. Also, to confirm maximum 250 milliamp current to the load, we need to connect a minimum load resistance, and that is RL min equal to V0 by I0 max. It comes out to be 60 ohm. Finally, we have prepared the table for different components required. For the transistor, the calculated values are like this. Similarly, for the Q2, for the Zener diode, for the all resistors, and for the load resistance RL. These measured values may not be available in laboratory, so you have to choose very close values as available in your laboratory. But in this design, we are going to use the measured values only, because we are going to check our circuit using some circuit simulators. We are now going to check our circuit using some circuit simulator. The design 1 we have checked using circuit maker. Now we are going to check our circuit for the design 2 using multisim. Design 1 we have used here using multisim also to check the rectifier characteristics. Before we proceed regulated power supply, let us check the performance of the circuit for the rectifier. We have to use one voltage source here. The peak to peak value of the voltage source has been set 314. Basically, this will provide 220 volt RMS. A transformer has been used. The transformer can be modeled. You can edit the transformer just by changing the value of L1, L2 and L3. You can change the trans ratio to obtain 20 volt unregulated voltage. That's why we have to set the L1, L2 and L3 value. L1, L2 and L3 values are the self inductances for the primary and secondary. We have used two diodes, D1 and D2, a capacitor and a bleeder resistors. Let us try to check the performance of this rectifier circuit. CRO has been connected with the inputs, that means transformer output and rectifier output. Let us try to check the performance. So this is the secondary output of the transformer, and this is the rectified output. You can check just by reducing the capacitance value. Let us take 1 microfarad. Now you can check the performance. The ripple is, again you can change the bleed resistance value also. Now check that ripple is more, so that's why you need the capacitance value more. At the same time, you have to connect a bleeder resistance with higher value. To check the performance of the circuit, you can connect the rectifier output with the regulated power supply. This is the circuit as per our calculation. Q1, Q2 value has been set. The resistance values are taken. The transistors are selected accordingly. The beta 1 value for the transistor 1 is 125. How to set that value? Just go to the edit model parameter. The forward beta is equal to 125. So you can set it. And similarly, the beta 2 value for the transistor Q2, which is the first transistor, it is 50. That also you can set it to 50. So we have connected one load of 10 kilo ohm. We can vary the load resistance as per our load requirement. We have connected two voltmeters to check unregulated voltage and another voltmeter to check regulated output. This has been connected to check the current flowing through this load. Now our circuit is ready to cross check its performance. So let us run the simulation. Now check what is the transient output. This is the unregulated voltage. This is regulated voltage, and this is the load current. Your unregulated voltage is 20.4 volt and regulated voltage is 14.916, which is very close to our desired value 15 volts. The load current is 1.5 milliampere. Let us set another load resistance value. Let us choose some load of resistance 100 ohm. Now see the difference. Unregulated voltage is very close to 19 volt, and the regulated voltage is very close to 15 volt also. The load current is very high, that's why we are not getting a regulation. If you increase the load resistance or if you decrease the load current, in that case you may get some better performance. The performance, just by setting 1 kilo ohm load, check the performance. Regulated output voltage is about 15 volt and unregulated voltage is 20. Everything as per our expectation. Now we want to check the line regulation performance of this regulator circuit. For that, let us use very higher value of load resistance. Let us take 100 kilo ohm. Output voltage very close to 15 volt. Now let us change the input source voltage. Let us make it 250 volt. Now check the performance. Now see, our peak to peak voltage is now 250 volt. Unregulated voltage is 17, but what we are getting? We are getting as per our expected value, which is very close to 15 volt. So line regulation performance has been checked perfectly. Our circuit design is very good. The performance can be checked using this table. You have to take different values of load current and output voltage, and you have to plot one graph like this, and you have to calculate the percentage of load regulation using this formula. And at the same time, you have to take the measurement for the line regulation also. For that, you have to vary the line voltage, and you have to note different output voltages corresponding to the line voltages. You have to measure percentage of regulation and percentage of regulation per volt. Graphically also you can plot this. So that's all.
In the end, you are assigned some jobs for different groups. In every job, you have to design a series regulated DC voltage supply, some specified output voltage with some rated load current.
So good luck, finish your job as early as possible.